Yep.
Alrighty, so first part of this lecture 2, what I want to do is I want to introduce you guys to the Fourier transform. I want to move beyond that to a discrete Fourier transform. That's just going to be the mathematics necessary to understand Shor's algorithm. Then what we're going to do is we're going to delve into a little bit of circuit analysis in the process and try to understand how the actual circuit of Shor's implements Shor's algorithm. But in order to really understand Shor's algorithm, because Shor's algorithm actually isn't that complex of an algorithm, once you understand something called the quantum Fourier transform. So that's going to require that we do a little bit of sidetrack to the discrete Fourier transform, and then I'm also going to need to present a little bit of number theory so you know how we can go from a factoring problem to a period finding problem. So all those steps individually aren't too bad. But obviously, them all being put together is where the difficulty lies, and why it's sometimes kind of hard to understand Shor's algorithm. Grover's algorithm has a nice geometric representation. I like to think this has a beautiful geometry associated to it as well, but I don't think it's as nice as Grover's algorithm to understand. So first, I'm not going to assume you guys know what a Fourier transform is, so I'm going to go on a little bit about why we care about defining such a thing, and a little bit of how we actually get the results. Especially because I feel like if we're going to go on a sidetrack of the discrete Fourier transform, the quantum Fourier transform, in order to really these things be called Fourier transforms, you need to understand what the idea of the Fourier transform really was. Otherwise, it's kind of hard to understand how the things relate to each other, and it just seems like we just slap quantum and discrete on top of something, which in essence you're going to see is they're all kind of minor extensions of Fourier transforms. But essentially the basic principle is we have sines and cosines. Those come up a lot. And we define sines and cosines basically from their amplitude and their frequency, right? This is something that, and they're offset, but we're going to assume we don't care about the offset for sake of argument, because we can just always recenter to a standard point, right? But right here I have a function. You can see here this is our little sine function right there. This is going to be our sine function f2, which is just twice the frequency, and you can see just there's twice the peaks and peaks and valleys. So right here they're separated by some distance, and I really want to define what this base is, because I think it's very hard to understand the Fourier transform for understanding what implicitly mathematically the space we're operating in. Right here, amplitude, right, just your normal one, time. And this is, from this perspective, where the red is what you normally see when you plot sine and cosine. However, usually if we're observing something that can be decomposed into a series of sines and cosines, and most of the time, one reason why we care about the Fourier transform is to find out what these constituting sines and cosines are. But let's just say, for the sake of argument, we know that our underlying representation is a series of, or at least we suspect that a family of sinusoidal functions can represent what we seek. In this case, this is the projection, what we actually see. And we're going to see it doesn't matter the fact that we're looking at the projection. Right here, when we project onto this axis, we get overall amplitude and time. So this is f1 plus f2. It's not exactly that surprising. It has this shape a little bit. This is if we project in the green area here, which is kind of just taking a view of, oh, there's two frequencies, that's where I see something. I don't see anything anywhere else. So the fact that there's these spikes here at exactly 2 pi and 4 pi shouldn't exactly give any source of confusion. I would just like to mention for for future considerations, especially the continuous variant of, quantum computing, if we're going to generalize the Fourier transform to that context specifically, our basis operators are position and momentum. So I figured that I say we can make the analogy of position being the same thing as time, and then if we do that, we get that, in this case, velocity squared, or momentum. Oh, not velocity, the derivative of position here. This is going to be dx dt, that's velocity. times applied mass, we get momentum. Now you can see it doesn't matter the fact if we consider momentum or we consider velocity, both of them would achieve the same thing. We usually pick momentum and position just because that our potentials are usually defined in terms of position, and our usually our kinetics are defined in terms of momentum. So that's more just, we choose to, you can think of it as we convert units. Right here, this is representing that. If we do this analogy at temperature, time to frequency, we get that the Fourier transform position gives us momentum and vice versa, with regards to the inverse. Now, I'm going to assume you guys know a little bit of multivariate here, enough to know what just a cross product is. In this case, I hat, j hat, and k hat are probably familiar ideas. In this case, I'm changing them slightly so that we have time as being I hat, f as being j hat, and a as being k hat. If you look at the figure, you would see in order to be consistent, this is the convention we're forced to take on. The reason why I do this is because it's going to make the next step a little bit more intuitive. So what we really want is, if we have a function of amplitude and time, what we really want is a function that tells us what the omegas are, right? The peaks of those associated omegas. So this is going to be, we're looking at it from the red, and we want the green right here, right? So what's one way of doing that? We just take two vectors in the perspective of of red, and we would get a vector within the perspective of f, or green in this case. So because of that, this is just making more explicit that assumption, t hat and a hat. Now, we're fortunate here, which is the fact that by definition, our amplitude from being one sinusoidal function, it can be defined as a function of our time. So here we just take time, t hat, crossed with a t of a hat, and this is going to give us our function of f hat of t in our f direction. Now, one thing I would say is we can just say sine omega t for our cross product there. Then we get t times a of t as in the f hat direction. And so this gets us one step closer to what we want. However, I said we did not want a function of t. In fact, we don't care what perspective of time we're considering, right? So because of that, we don't want to bias to any specific perspective, but if there exists a time in which it has a value, we want to consider, we're asking the question of, throughout the whole time, does this function exist? Is there a disturbance? So in this case, that's simply solved by integrating with respect to time. This does the time as we want. Right here we have a of t is right there, and our sine omega t. Now, the one consideration is we have to account for the fact that our function can have complex values. This is a simple modification because, especially if you have any physics background, it would seem very intuitive to replace sine omega t with e to the imaginary unit omega t, because that is Euler's formula. You get it being sine, plus I, cosine of the same argument. So that's what we want. And we do that, and if you actually recall from one of your classes, you might have heard Fourier transform mentioned before. This is the equation that you get as being the Fourier transform. And its inverse now makes a lot of sense, because all we would do in this process is we'll basically start off from this step, but we'll just take a negative sign, right? And we'll just curl with respect to the other one, don't curl with respect to that one. And if you look geometrically and use your right-hand rule, you would see you're forced to take on a negative sign. So that's why we have the negative right here, and the negative I omega t, as opposed to anything else. So that's kind of the reason for the symmetry between the Fourier transform and its inverse function, and how we actually derive the Fourier transform in general. So the reason why I mention this is because, in this derivation in particular, is because I think it's going to help us a lot with trying to understand what this means intuitively in more discrete space. And if you want to get a more this is a nice argument, but the one thing that it presupposes is that your function is decomposable into it. The Fourier's theorem and for which the formula derives was a little bit more expansive in the sense that saying all functions can be represented as an infinite series of sinusoidal functions or projected onto that space. So it actually has a different derivation. This is kind of good if you accept the principle that that's true. So this is not actually how it was derived. Free Blue, One Brown has an excellent video if you want to see the actual motivation, which I hate to say it, this is what you're going to read in a math textbook as the proof. It's a straightforward derivation. No one's really going to argue any aspect of it, but it's not very that motivating. You know, it's hard to think that you would come up with caring about this problem in particular. But say Levy, I'm going to do this one in a little bit more parts, mostly because of upload time, and also because I think it's easier to be a little bit more on track when we're trying to make 10-minute segments.